Well, it's time to write up some more solutions. And again, may as well record it. And it seems like some of you enjoyed this little experiment to have it video recorded, so I figured I'd try it again. Okay, so I've got my text editor open, I've got the homework open. It's been a little while since I've looked at the homework, so not sure how this will go exactly, or how long it will take. Hopefully it'll be about an hour, but that's what I said last time. So anyway, let's see, let's start. The first thing I need to do is change this to say solutions. And then read the first problem. So we're supposed to compute the quotient and remainder for 1,000 divided by 89. So we're supposed to find the quotient and the remainder. And we need to make sure that it actually is a quotient remainder, so that involves knowing what the definition of, well, what division is. So one thing is, we don't really need to do this longhand. We just need to know how this is supposed to work. So I'm going to pull up Mathematica. Here's just some random Mathematica session. And so it's supposed to be 1,000 by 89. One thing I can do is take the floor of this. So it's going to be 11 for that. And again, we could have found this by hand very easily. I'm just being a little lazy since, I get to write the solutions the way I want. The other thing is we need the remainder, so may as well use the mod function for that. And so that's 21. And what we need to check is that if we take 89 times the quotient and add the remainder, that we do indeed get 1,000, and do we? Great. So let's copy these in. Okay, and also we have to create a solution. So let's see, how should I say this? Well, because do I want to show how you might compute it? Because like to find this, the way it would work, it's just long division, which you learned in grade school. So anyway, so we calculate that L floor 1,000 over 89 R floor equals 11, and 1,000 remainder 89. And remainder, by the way, is a command I created, if you like doing LaTeX. It's just math bin of \%, and math bin is a binary operator in math mode. So we got 21. Calculate it by, well, let's not say how we found it. And then so we can check that 1,000 equals the quotient, which is 11, times, using C dot because that's the classy way, 11 times what were we dividing by, 89, plus the remainder, which is 21, and 2, that it's actually a valid remainder, which is that it's at least as large as 0, so that is 21, and it's strictly less than what we divided by. So let's see how that looks. Okay, well, and I'll say, so it oops, we need to see what we're typing. So it satisfies the two conclusions of the division algorithm. I don't like that. So this is just like not a math thing, but I don't like that line break right there. So let's just turn this into an enumerate. takes a little more space, but it'll probably look good. No comma there for proper English. Okay, I guess it's A and B. I'm fine with that. Okay, so that's good enough. Okay, so let's calculate the GCD of 89 and 144 using the Euclidean algorithm. Let's create some solution environments. So this is a somewhat tedious calculation, but it's not so bad. So we can, let's see, I'll do this with an align environment, and we have 89, 144 is 89, 144 remainder 89, because you can always take either of the arguments of a GCD and take its remainder with respect to the other one. And then that's 89, and not too, well, I'm not going to do the mental arithmetic. I think it's like, I think the quotient's probably 2, so let's see, 140, nope, it's 1. So I got a negative number when I subtracted 2 89s, but if I subtract 1 89, I get a positive number, so that has to be the remainder. So that's that. So again, we can take the other number. Oh, right. So looking ahead, the next problem is we want to find the integers where the GCD is 89 times x plus 144 times y. So we do need to remember how we did all these divisions. So I guess I'll record them here in Mathematica to get the quotients and the remainders, because those are going to come in handy. Okay, so 55, 89, remainder 55, and I think that's going to be again 89 minus 55. Let's see what, well, 2 times 55 is more than 100, so it's going to be 1 times, so 34. And then 55, okay, so then the next one, we'll swap them and then do 55 mod 34. And so that would be 34, and I'm pretty sure that 1 will be the right number for what the quotient is. So then what is the remainder? 21. And we know that's a remainder because it's between 0 and 33 inclusive. Why did I do this problem? So this, just to give you some context, these are Fibonacci numbers, and Fibonacci numbers actually have the maximally long Euclidean algorithm, and all the numbers we get are all the Fibonacci numbers all the way down. Well, let's keep going. So let's see, 34 minus 1 times 21 is 13. And then 13, 21, remainder 13 is equal to 13. And then we're going to again subtract 1 times 13 to get the remainder, which is 8. That's a good remainder. Okay, 8, 13, remainder 8 is 8, and then, like, this is where I can, wait, oh, 13, okay, I'm able to do this mental arithmetic now. Then 5, 8, remainder 5 is equal to 5, 3, at this point, it is sort of, it's obvious what the GCD is because these are both primes and they're different. But let's just stick to the program here. So this would be 3, 2, and then 2, 3, remainder 2 is 2, 1. And the question is, do we just stop here because the remainder of 2 and 1 is 2? Or do we get to the point where it's 0? Let's go one more step. Like, we do have a lot of freedom for how we carry out this algorithm. Oops, that's 1. Oh wait, did I say 2 earlier? I meant it's obviously 1, because one of the two things in the GCD divides the other, the 1 does, and so that's the absolute value of it would be the GCD. So that's 1, 0, and then that's 1. Let's add some text to set things up. So we calculate the GCD using the Euclidean algorithm. Therefore, the GCD is 1. I'm going to add a little note here for all these quotients. Note, in each case, the remainder Q rem R. No, what do I want to say? I'll put this in the next part. So let's see how this looks so far, because that was a lot without checking. So let's see, we calculate the GCD using the Euclidean algorithm, and then we just have this long calculation with way too many steps. But we get 1, which is what we'd expect, I suppose. Though I know that's 12 times 12, but anyway, so we got 1. Well, let's just check, because why not? We have a computer. So the GCD of 89 and 144, 1, great. So now we want to find these integers x and y such that the GCD is 89 times x plus 144 times y. So yeah, and so we need to do this sort of in reverse. There are a few ways to calculate this. This is just the one that, the way I like to do it. So note that in each case, so note that in each division in the above calculation, the quotient was 1. So for example, 144 remainder 89 is 144 minus 1 c dot 89. Yeah, so because what we're wanting to do is start from the end where it's easy to write 1 in terms of the numbers in the GCD, and then start substituting these expressions from doing division back in. So hence, okay, now this is where we start up a mysterious calculation, but we know what we're trying to do, so in the end we'll just have what we want. So 1 is equal to, well, I guess let's start at the very end. Okay, so just let's look at what we have. Okay, so 1, I have to collect my thoughts. Okay, 0 was 2 mod 1, right? So let's write this out in excruciating detail. So what we're going to do is we're going to keep recognizing the second number in these sums as being one of the remainders that we calculated. So 2 mod 1 is it's very silly starting from this point when it's 0. It just seems like this is not a very useful part of the calculation. So what do I want to do? Yeah, and also we can choose any coefficient here that we want. Okay, let's just start at 2, 1. Now, we're doing this in excruciating detail. That's what I said. So we're going to do it. So 2 remainder 1 was 2 minus 2 c dot 1. Okay, so I substituted in the other part of division. Wait, what am I doing? Wait, what's this one special? I guess, oh no, that one's the special one. All the others, the quotient is 1. But 2 divided by 1, of course, the quotient is 2. Which just makes explaining this a little odd. Oh, why do basic things cause so much trouble sometimes? So how do I want to do this? Let's not go to the very end, just because it actually makes things awkward. Now let's do it. So let's note that for each division in the above calculation, with the exception of 2 divided that's a little rhetorical trick. So with the exception of 2 divided by 1, the quotient was 1. Okay, so let's continue. So yeah, so 2 mod 1, that was 2 minus 2 times 1. And now what we do is we treat the second number, so that's going to be a second number. It's 1 times 2. And we're going to collect terms. So we have 0 c dot 2. And then there's a 1 and a minus 2 times 1. So that's minus 1 c dot 1. Okay, so we're treating 2 and 1 as like the things that have coefficients. But this is, wait, what am I doing? Oh, there's a 0 out front, of course. See, this is why starting from this point is really awkward. What I really just want to start here and say that 1 is 0 times 2 plus 1 times 1, which is where we are right now. Anyway, so that was sort of a useless thing, but at least we're going through the program here. Okay, so now, what's 1? It comes from 3 mod 2. And what's, so, and 3 mod 2 was 1 times 3, or just 3, minus 1 c dot 2. Okay, so 3 mod 2 is 3 minus 1 times 2, because 1 is the quotient. Okay. So now we combine like terms where the 2's and 3's are now the things that have coefficients. So we have 1 times 3, and there's 0 2's here and minus 1 2's there. Okay, so 1 times 3 minus 1 times 2 is 1. A lot of work for that very basic fact. Like, really, we could have just started there. But it doesn't really matter because we're calculating the right thing. So now, what was 2? 2 is 5 mod 3. So 1 times 3 minus 1 times 5 mod 3 is 1 c dot 3 minus 1 c dot 5 minus 1 c dot 3. Yeah. And then let's look at what we have. So we take the terms that we have. So there's minus 1, 5. And then there's 1, 3, and then the negative 3. So then that's plus 1 c dot, no, plus 2 3s. And 6 minus 5 is 1. Okay, great. What I'm going to do here is everything's going to be basically the same. So let's copy paste and just change numbers so that it looks, so it's correct for our situation. So what's 3? 3 is 8 mod 5. 8 mod 5. And then, so we have minus 1 times 5 minus, plus 2 times 8 mod 5 was 8 minus 1 times 5. Okay, just going to copy the line, change the numbers, so it's going to be slightly wrong until it's all fixed. So how many 8s? 2 8s. How many 5s? We have minus 2, minus 1, so minus 3 5s. And 16 minus 15, that's 1. Okay. So 2, 8 minus 3. Okay, so 5 was 13 mod 8. Oh, this is a tedious problem to type, but it's not so bad on paper. Okay, minus 3 times 13 minus 1 times 8. Okay, nice so far. Okay, so now let's collect terms. We have minus 3 13s. And how many 8s? 2 and 4, so 5 8s. Now I'm wondering, now that it's looking like this, the question is this going to be useful for anyone to ever look at? Because it just feels like a run-on sentence. It'd be nice if all, like, at least the equals were lined up, but maybe I'll do that later. Or do I just not need this mod part? Or maybe from now on I just put some dots. Or I just continue because we're halfway there. Okay, let's just continue. So 8, that was what mod what? It was 21 mod 3. 13, I mean. And that is 521 minus 1 times 13. Oh, wait, you know, maybe one thing that's really cluttering it up is these extraneous c dots. Yeah, messing around with LaTeX is a great way to avoid actually working on problems if you're not having, the most fun with them. So let's just remove these C dots and it's a little break. I don't know. Okay, so we've written what that remainder was. Okay, so now how many 21s? We have 5 21s. And how many 13s? We have -5 -3 -8 13s. Is it cheating to just be like, we notice a pattern? So look at what these coefficients are. 1, 2, 3, 5. Look at this, 1, 2, 3, 5. Of course, it's going positive, negative, positive, negative, positive. But let's yeah, sorry, I'm getting tired of just typing this up. So let's do dots, or L dots for lower dots. And then let's do an intertext. And continuing in this way, we get, I think I need a double backslash for this to work right. So it's going to be something C dot, what are our numbers? 144 plus something C dot 89. So let's fill these in. So 21, 13, 8, 5. Is that how that goes? So 21, 13, 8, 5? So then 140, let's see, what was the order? 21, 13. So it's like kind of interleaved in this odd way. So, so 144, 89, 55, 34. So those are the numbers. They have to be. I already forgot them. Okay, so the bigger number gets the smaller one, so 34. And then the smaller number gets the bigger one, which is 55. And now we have to decide whether it's positive or negative. So it goes positive, negative, starting with 3. Positive, negative, oh wait, positive, negative, positive, negative, positive, negative, positive, negative, and that would be positive, I think. And each one gets opposite sign. Let's check. So, let's see, 34 times 144 minus 55 times 89? Yes, 1. Okay, so it's a lie that we continued in this way, but if we continue in this way, this is what we have to get, which we could prove by actually carrying it out. That feels like cheating. Well, I guess if you feel like it's cheating, let me know. So maybe C dots would look better. No, but I'll just leave it. Okay, so what was the question? So we wanted to find, okay, so therefore, with x equals minus 55 and y equals 34, we have 89, 144 equals 89x plus 144y. Okay, well, this is soaked up half an hour. These okay, well anyway, I guess if there's anything to learn from this, and this was not how I intended it to be solved. I just meant for you to just do it, go through. But sometimes it pays to see the pattern, and or like guess a pattern and see if it actually worked. Like, so one thing is, we don't need, the only proof we need that these are some, like we just want some integers, right? So any method that you do to get two integers is fine. And we checked that this really is 1, so, you know, we did it. The only cheating part is, like, we didn't completely follow the hint, but it's just a hint, right? Okay, let's find a prime power factorization. Let's remove the footnote. Add a solution. Okay, so one thing is, theoretically, there's a unique one. So it doesn't matter how we find the prime power factorization. And so one question is, how much do we have to do this by hand? So let's just right, one thing I wanted to show you is that Mathematica is able to do extended GCD, and this is something you can even type into Wolfram Alpha, this exact expression, because Wolfram Alpha is based on Mathematica. It's all written in it. So it says that the GCD of 89 and 144 is 1, and minus 5 times 89 plus 34 times 144 is 1, according to it. Yeah, so that happens to match what we found, so that's good. I guess it used the same algorithm. Okay, so let's do this by hand, showing some work, but like it really is fine just giving it and showing that that's correct. So 121 680. Okay. So we see it ends in 0, so it is a multiple of 10, which is 2 times 5. So we only need to prime factorize one to 168. This number is even, so it's a multiple of 2, and so dividing by 2, we get, this shouldn't be too hard to, okay, well it's going to end in a 4, I think. Oh, it's 12, 16, 8. So it's like 06, 08, 4. That times 2 would be that. This 2 is a multiple of 2. And dividing by 2 again, we get 3042. It's nice when basically each digit is divisible, so you can just divide. Okay. Oh, this one is also divisible by 2. Again, this is divisible by 2. So dividing, we get 1521. Now, the sum of the digits here is 3. I mean, it's 0 mod 3. So it's divisible by 3. And really, what I'm seeing is 15 and 21. Both of those are divisible by 3. So 15 by 3 is 5. Well, so it's 05 and 21 is 07. So 507. And now's a good time just to make sure that things are going all right. So 507 times 3 times 2 times 2, 6084, that's good, times 2 times 5. Wait, what just happened? Oh, there you go. Oh, maybe there's another. Oh, okay. I missed a 2. Okay, so far so good. We've got all these primes, and we've got this 507. 7. Oh, that is divisible by 3. I guess I'm using, so this divisibility trick I think might be coming from after this lecture, but the point is, like, if we just keep trying to divide by small primes, like 3, like this is not divisible by 2, so what we should be doing is divide by 3 repeatedly now. And so this is just a trick to see that it is divisible without needing to divide it and check the remainder. So it's divisible by 3. So dividing by 3, we get so let's see, 3 times 100 is 300, which leaves 200. And I'm just gonna cheat, I'm sorry. So 507 divided by 3, 169. And maybe you recognize, you might not have learned times tables at to 13, but I happen to know like 13 squared is 169. So let's set this out as a display style. 12168 is equal to, okay, so 507 we just saw was 3, and then times 13 squared. Okay, so 121,680 is 2 to the power of 1, 2, 3, 4. 3 to the power of 2, 5, 13 squared. So this is anyway just like how I was thinking about how to do it. They're just like, you know, a bucket of techniques. So I'll mention so alternatively we could have repeatedly divided by small primes in order. Because that's like more of the algorithm. Yeah, so then we would have needed to try dividing by 7. Okay, so now let's give word P for all primes P. So, all right, how do I create a table? I think it's tabular format. I'm going to do C. Okay, how many primes? 2, 3, 5, 7, 13, and the rest. So 1, 2, 3, 4, 5. Maybe I'll need more. So here's what I'm doing. I'm creating, oh, I should also center it. I'm going to actually make this right aligned. So I'm just making a little table of what ord is for each of these primes. So 2, 3, 5, 7, 13, and greater than 13. Well, what's the next prime? Just to, so 13, 14, 15, 16, 17? Okay, so ord, remember, is the multiplicity of the prime in the factorization. That's what the theorem ended up being. So for 2, that's 4, because that's its power. And then for 3, that's 2. That's its power. 5 was, it's 5 to the 1. And then 7, there are no 7s. 13, there are 2 of those. And then it's 0 for everything else, because no other primes appear. Okay, so here is a table listing the ord for each prime. I wonder if that little space is, there's a space with the inequality. I wonder if that's something that can be gotten rid of. Oh, that's fine. Okay. Now 4, let's solve an equation. Give a description for the set of all integer solutions to 3x plus 4y equals 15. So first, let's check that there is a solution. At all. The condition is that the GCD of 3 and 4 divides 15. And since the GCD of 3 and 4 is 1, because this is 2 squared, that's 3, nothing in common, this holds. So now what do we do? Well, there's a theorem in lecture which gives the solution set. So using, so we have this set of solutions, which is I don't even know if I need those as left and right, but okay, so and I should say that they're pairs. So how did this work? We're supposed to take 15 divided by the GCD. I guess I should think about what the lecture said. Because it's supposed to, right, So it's 15 divided by the GCD, and then we multiply by various k, and then multiply by -4 for x and 3 for y. Okay. So minus frac minus 4k. Oh wait, no, sorry. I was giving the homogeneous solution. Okay, so let's give the solution. So, well, first of all, we can just find some solution. So let's see. Can we just find one? So, well, 3 times 5 plus 4 times 0 is, oh wait, yeah, that's 15. So in fact, since 3 divides 15, we have at least one solution. xy equals 5, 0. Okay, so now the idea was we take the homogeneous solution and add it to the particular solution. So we take 5 plus this homogeneous solution, so minus 4k over the GCD, 0 plus frac 3k over the GCD. And let's also verify that this does work, because while the lecture said that, you know, we need to make sure we believe it. And then, let's see, does that compile? Nope, I forgot to put backslashes for my curly braces. Okay, so let's check that there's a solution and all. So, you know, this statement, it's unnecessary because we just wrote down a solution. So, you know, there's that. But now, okay, so we've got this. So what we want to check is that if we substitute in minus 4 over 1, 3 over 1, we get 0. And so 3 times minus 4 plus 4 times 3, those cancel out, and that's 0. So those indeed are homogeneous solutions. Yeah, and then, anyway, so we got that. And we may as well simplify it. And let's say how we got that, which is from adding the particular solution 5, 0 to each homogeneous solution for 3x plus 4y equals 0. For sake of simplification, the solution set is equivalently given by, okay, let's copy paste. Okay, so 3, 4, that was 1, so no need to have that. And then adding 0, you know, y. Okay. That is our solution. That's fine, a little space. What are you doing there? Well, one way is we don't actually need the left and right anymore. All left and right do is make everything big to make delimiters big to encompass. Oh wow, I forgot that. That should be big too. To encompass its contents. So now It's small, and I guess it decided it doesn't need quite so much space. That seems to be a little bug in LaTeX. I think it's middle. Of course, it's not so easy. It might be middle bar. But then the spacing is not right. I think semicolon spacing is correct. Okay, so great, there's that. So now we want to find the two natural number solutions. How nice of the author of this homework to tell you that there are only two. So also, I guess that answers whether there's a solution, but you know, can't always trust whoever wrote the questions. So 3x plus 4y equals 15. So we got this. So it suffices, given the solution set from before, it suffices to, well, solve. We want both of the components to be non-negative. So we want to solve this pair of inequalities. The second inequality, by dividing by 3, is equivalently 0 is less than k, or equal to k. So that means we can just start plugging in values of k until the first inequality fails. But let's also manipulate the first one just for clarity. And the first inequality, by adding 4k, is equivalently 4k is less than or equal to 5. By adding 4k and dividing by 4, hence 0 is less than or equal to k is less than or equal to 5/4. The only integers that solve this are k in 0, 1, because 5/4 is just a bit more than 1. So plugging these values of k in, we get the two natural number solutions. xy to 3x plus 4y equals 15, which are well, I guess I have to actually calculate now. So let's put 0 in. That's 5, 0. So quad is a quad space, 4 spaces. It's a nice little thing. Maybe it will look good. Let's plug in 1 now. So that's 1, 5 minus 4, 3. Period. Okay. So let's check it's actually a solution. Always a good thing. So 1 times 3 is 3, 4 times 3 is 12, and 12 plus 3 is 15. Cool. Okay, last problem for 4. So find all the solutions to this. So let's just check. Solutions exist, or the solution set is non-empty if and only if the GCD of 6 and 4 divides 15, but 6 and 4, the GCD is 2. And 2, I think it's n mid 15. So therefore, the solution set is the empty set. Oh yeah, I've never liked that particular symbol for the empty set. Okay, so now we've done problems 1 and 2 and 3. Oh, and 4. Cool. So far it's been 55 minutes. I guess I doubt we can finish the rest in 5 minutes to make it just an hour. Okay, but 5, this is actually a not so bad problem. Okay, so prove or disprove. For all a, b, c, and d, if a divides b and c divides d, then ac divides bd. One reason that we should believe this is that the prime factors of b and d consist of all the prime factors of b and d. And also, a and c has all the same prime factors as a and c combined. And so all the prime factors of a and c should then show up in b and d. So we're going to prove it. So suppose a, b, c, d are integers are such that a mid b and c mid d. We will show that ac divides bd. Okay, so by definition of divisibility, there exists k and h in the integers such that a times k, well, ka equals b, and hc equals d. Multiply. Yeah, I'm sort of just doing this automatically. So really, like, we don't really have anything to deal with the divisibility other than the definition. And so, like for AC divides BD, we want to show that something times AC equals BD. So we got these two equations, and if we multiply them together, so multiply, or we see, or doing it this other way, we see that KH AC is equal to, let's do some rearranging here. So KAHC, which is equal to BD, and therefore, by the definition of divisibility, AC divides BD, which is what we wanted to show. Let's also turn this into a proof. Oops, I accidentally italicized it. So as a proof, we get the nice little proof box, the Halmos, because Halmos popularized it. It's also known as a tombstone from magazine publishing. Okay, so that was that. Okay, I need to go for now, and I will be back later to finish this up. I guess you won't notice anything other than a scene change, potentially. Yeah, anyway, see you soon. Well, time has passed, as you can see behind me. Let's see, where were we? So we showed this number 5 was true, and proved it. So now number 6. We're supposed to consider this proposition, come up with 3 illuminating examples for it, and prove it. So let's see. So an illuminating example, let's see, one probably, because I guess the idea with a math statement is, you know, it is a thing that's just true or false, but sometimes it's nice to get some intuition. So let's see, itemize Yeah. So I'm just going to create a list here. What's one example? Well, if a is 0, then it's certainly true. Let's do I guess for an illuminating example, we probably want m and n to be some concrete numbers too. But yeah, I'll just choose some numbers. I just want to be illuminating. It's because, okay, so one thing is, if a is 0, then both of these remainders are going to be 0, because that's how remainders work. If n equals m, then this left-hand side collapses, so that seems illuminating. What else? Also, we want a case where like n and m are like some multiple of each other. So I'll do both a sort of a generic example and ones with concrete values. So a mod n mod m equals 0 remainder and remainder n m, which is 0 remainder m. Yeah. Let's see, what else? For example, when m equals 5 and n equals 10, then this is that 0 remainder 10 remainder 5 is 0 remainder 5. Let's add if to make that a sentence. Okay, maybe that counts as illuminating. What's another example that I came up with? That was, oh, if m equals n. So a remainder m equals a remainder m. For example, if m equals 5 and a equals 2, then this is that 2 remainder 5 remainder 5 equals 2 remainder 5. I guess I did not demonstrate this. Oh right, I only need to demonstrate it for the concrete numbers. And I guess it's sort of just you calculate it. I could also prove it for these other cases, because these ones aren't so hard to prove. Anyway, those are... Okay, as you can check by calculation. Maybe not you, let's just say 1. Like you just type it into a computer, like here. You know, mod 0. Actually, I think Mathematicon can do this. Like, oh no, it doesn't. It's not sure about that. So I'm just playing around here, but I want to see if it can figure out that if n is positive, that, oh yeah, it can. What if m is positive. Okay, so if you give it a couple assumptions, the simplifier routine is able to figure this out. What about this? Nah, it's not that smart. I would have expected, a mod n. Oh, I was just going to calculate these. Well, there's mod, a computer can calculate mod. I can just plug them in. I'll need to say more than that. Okay, and now I want one where I feel like 3 is actually too many. I guess one thing is, no, 3 is too many. Sorry about that. Hopefully you didn't get too stressed out trying to be really illuminating. So let's just choose like a is 2, m equals 5, and n equals 10. Then 2 remainder 10. Oh, it can be more illuminating. Let's do 22. So 22 remainder 10 remainder 5 is equal to, well, 2 remainder 5, and 22 remainder 5 is equal to, well, 2. And 2 remainder 5 is 2. Okay. That seems good enough to me. It's enough to at least make me believe it, I guess. Or believe that might be possible for this to be true. So, like, I guess what we want to do with an example like this, like what makes something illuminating, we're trying to come up with numbers that would show that it isn't true. So I chose 22 because it's bigger than the 2, and so there's going to be some wraparound. And it's also good to check that when the numbers are the same, like the simplest kind of divisibility, then it holds. And then also it better work for 0, right? Okay, let's prove this proposition. So let's suppose that a, m, n are integers. So we're introducing our variables and hypotheses such that m is greater than 0, n is greater than 0, and m divides n. Now I think I'm supposed to be doing div. Is there a difference between div and mid? Guess. Oh, yes. Div is the division sign. Okay. We will show that a remainder n remainder m equals a remainder m. So for this, if I remember, it pays to think about how the division algorithm works. Like, we want to show that this first number can stand in place of the second number. So it suffices to show that 1 that, let's see, a equals by the division algorithm, it suffices to show that a equals the quotient q, show that for some q in z, that a equals q times, what are we dividing by, m plus this thing, and 0 is less than or equal to that thing is less than m. Right? Because that means that by the division algorithm, q is the quotient in this expression, and this number, whatever it is the remainder. And by uniqueness of division, that means this number would equal this number. Okay. It's really an oblique sort of thought to have for a way to prove something, but it's one of those things that you get used to coming up with. Okay, so that's what we want to do, and the thing is, this is a remainder already, so that's just true. So it's the remainder after dividing a by n, or a remainder n by m. So this inequality holds. So it holds by definition of division. Thus, it suffices to show that, I'll just repeat this, the one part that we need. Okay. Now how are we going to do this? Because I haven't thought of, like, we need to choose q basically, and I don't really know what q is off the top of my head. And then we might need to poke around a little. Well, presumably it's going to be the quotient of a divided by m, right? Well, here's something we can do. So, let's use one of the ways of representing a remainder, which is a minus the quotient of a rem n by m. Doesn't really matter what this number is, it will turn out, I'm pretty sure. So there's some number that we can subtract, or some multiple of m we can subtract from a to get this remainder. Oh wait, is that it? Okay. Yeah, let's rearrange this. Okay. So, like, I was just thinking about how remainders, you can get them by doing the subtraction, but if we add this to both sides, then that's exactly what we want to show. So let's let q be this number. So let's use q equals this quotient. So it suffices to show that a equals q m plus this. And this is true since Well, this is the equation for division. Okay. So the definition of well, this is one of the properties for our. How do I want to say this? Some linguistic awkwardness. Let's just compile, collect our thoughts. So so using Q being that, it suffices to show this, and it's true since, well, this is how those two notations are defined. Like, they're defined to be the numbers that satisfy this, while this second number lies in a particular range. So that's that. Oh, I want this to be in a solution box, don't I? Okay, let's just read through again. So we suppose that a, m, and n are integers. Get that, those are the right hypotheses, and we want to show this. By the division algorithm, it suffices to show for some q that we want this to be the remainder, so it has the two properties. Since then, by uniqueness of division, we would have that this number that we have on hand is the remainder, using that symbol. Then since it's the remainder after dividing that by that, oh, I guess I could simplify this more. Okay. Since that is the remainder after dividing... Oh, wait, what am I saying? I'm tired. What am I doing? Because this is not the definition. Okay, let's try this again. So we still need to find that Q. Okay, that inequality is fine. Okay, that goal is fine. So we have that right. Let's go back a few minutes. We have that this remainder, by definition, is this floor expression times m, and subtracting that from a remainder n, right? So okay, we got that. And then that expression, the remainder, right, that's right there. Oh. Yeah, okay, so here's something that I should have been thinking about. Where did we use that m divides n? That is something that is a hypothesis, And also, so for illuminating examples, we really should have had one which shows that it's not true for m not dividing n. And that's pretty easy to cook up. Yeah, because non-examples are good. Like for example, if m is 5 and n is 7, so that fails there. And if a is, I don't know, 10, then a mod, or 10 mod 7 is 3, mod 5 is 3, but 10 mod 3 is 1. So those two numbers are different. So we definitely need to use that. So let's, using the definition of divisibility, let k and z be such that n equals km. So I want to get rid of that n. Okay, so again, using this idea for, let's see, rewriting, so a divided by n, let's see. Okay, so a mod n is a minus some division times n, and then minus that still. And then we can take this and replace, I want to replace this, I don't care about what the quotients are, I just want to get this m on the outside. Oops, where did we go? So I did that, and then what I see is I can take the a, and then I can take this expression without the m, and this expression without the m, okay, this is good because this is q. This is how it goes. Hence, let's just write it out nicely. We have a is equal to this times m plus this. Therefore, by using q equals this thing in the parentheses, we obtain the desired conclusion. Okay, so up to here was fine as when we were reading it. So using the definition of divisibility, let k be such that n equals km, and we have that a mod n mod m is a mod n, the thing we're dividing by m, minus the quotient by m, and then we do the same, a minus the quotient a by n times n, subtracting the old thing, replace n, factor out the m. Of course I made a little mistake there. The of course is just, you know, given how it's been going so far. Uh-oh, there's a little LaTeX error. Guess I forgot to put a right. Well, that was a guess. I guess I was wrong. Oh, I forgot another. Okay. Put a right to balance those big parentheses. And they're not big at all, so there's no need for that. Okay, so got the minus minus, turns into a plus. And so we put this onto the other side. So then a is that quotient times m plus this remainder. And so we get what we want. Okay, I just want to make sure I said something right. So Yeah, okay. So that's that. This sort of manipulation is a nice one for, like, now that we're doing modular arithmetic, you might be able to notice that what we're doing is we're kind of sloughing off these multiples of m, and those are all, well, we disregard those when we do things modulo m. So, but when we don't have congruence, like right here, then we need to keep track of all the things that we've sloughed off. But then this is saying that a mod n mod m is congruent to a mod m, which really is what we were trying to show. Yeah, because then a mod m is congruent to a mod m, or a remainder m. Okay, so that's that. Prove or disprove. For all a and n in the integers such that n is positive, then minus a mod n is a mod n. So let's come up with some examples. Let's see, what if a is 1 and n is 2? So then that's minus 1 mod 2. And, well, minus 1 mod 2, that ends up being 1. And 1 mod 2, that's 1. Well, okay, it's true for that. What about 0 for a? So minus 0 mod n, whatever n is going to be 0. And that's 0, so I guess that works. So far it seems like it can be possibly proved. Let's try 1 and 3. So minus 1 mod 3 is, well, we can add 3 to that to get a positive number, so that's 2 mod 3, which is 2. And then 1 mod 3 is 1. Okay, so 2 is not 1, so this has to be false, so we have to disprove it. Yeah. Also, I knew all the ways that it could look like it's true, so, I knew I had to disprove it. So hopefully you enjoyed that little show of ignorance, of pretend ignorance. Okay, so let's see. So we want to disprove it, right? So, oh right, we have 1 and 3. Well, this is not true. If a equals 1 and n equals 3, then we have that n equals greater than 0, but minus a remainder n is minus 1 remainder 3, which is 2, and a remainder n is 1 remainder 3, which is 1. Let's just point it out, yet 2 is not equal to 1. Okay, that's a disproof. So just a comment. To disprove it, what we're sort of actually doing is proving the we're proving the logical negation. Let's see, does bold look good? Nah, let's emphasize, italicize. Okay, so what is that logical negation? So it's, okay, so one thing to note is that when you have a for all such that, it's actually for all a and n in the integer, well, it's for all a an integer and for all m and n an integer. If n is greater than 0, then the conclusion. And when we logically negate for alls, they become there exists, and then we negate the inside. And when we logically negate an implication like this, it turns into the first thing is true and the second thing is false. So there exists a and n in the integers such that n is greater than 0 and minus a remainder n is not equal to a remainder n. So by choosing by choosing values for a and n, we can simply observe that it's true. And that's the proof. Just wanted to point that out, that we are proving something here. It's easy to write the proof of the opposite, because to prove that there exists, you just have to show that there exists something, and a good way to do that a lot of times is to just give a thing. Okay, so let's prove this next one. And also, okay, so this is if we have a quadratic polynomial, and if x is an integer root, then x has to divide the constant term. This is a really nifty way for finding roots of polynomials, at least if you want the root to be an integer. You take the constant term, and this is also true not just for quadratics, it's true for all orders, which is a nice thing. You take all the factors of the constant term, and you can just check if and there's only finitely many, right? So you check whether they're roots. And if none of the factors are roots, then this has no integer roots. So that can be a useful trick. Okay, so let's suppose that a, b, and x are in the integers. And we're assuming that x is a root of this polynomial. So we want to show that x divides b. And one thing to note is we can solve for b in that equation. Maybe that's useful. So b is minus x squared plus minus ax, which is equal to, well, there's a factor of x, that's probably important. So that's x times minus x squared minus a. Well, so that's the definition of divisibility. Because minus x squared minus a is the factor we're using. Hopefully that wasn't unnervingly short of a problem. Just thinking, I think there are some other conditions on that term. That we could probably come up with. Anyway, let's just continue. I can't stop thinking about, like, what would that be? So, well, let's just, I don't know if this will be included, but I think it's useful to think about it. Let's look at an example first. So here's a simple polynomial. So that is plus x minus 6. So see, like 2 and 3 are the, well, minus 2 and, well, 2 and minus 3 are the roots, and they both divide minus 6. So that's good that that works. put those in order. There's no reason to, but who doesn't like examples? I guess what I was thinking is, when we do have the roots, the sum of them, well, the negative sum of them is the coefficient in front of here. And it probably means that there's like some upper bound you could write for it. Anyway, okay, so let's look at this one. So when n is positive, we want the GCD of the number and its successor. What if it's important that it's positive? What if it's 0? That's 0 and 1? That's still 1. So that's a little suspicious. It also seems like, well, now that we know about mod, if we take these numbers mod 2, if this is even, that's odd, and if that's odd, that's even. So they don't have any factors in common. Also, if two numbers have factors in common, they're going to be different by a multiple of that factor. So these are only different by 1. So, like, how can they be like different by a multiple of, say, 7? So this seems like it should be true. Let's prove it. And I think we can actually just, okay, this is a simple one. So let's suppose that n is in n is positive. There's really no need for it to be positive. I think I know why I did that. I made it so that this problem was a little easier if you did it in a certain way. But we call that for all k in the integers, the GCD of n and n plus 1 is equal to the GCD of n and n plus 1 plus kn. It's that replacement rule. So adding some multiple of the first number to the second. So let's use k equals minus 1, because that will cancel the n out. So then we get n plus 1 is equal to n1. And the GCD of n and 1 is just 1, right? Because the only divisor of 1 is 1 and minus 1. Okay. And let's just, for sake of formality, say that we will show that n plus 1 equals 1. So that's that. And let's wrap it in a proof. See how that looks. Okay. Let's do an alternative proof for the fun of it. And I think there's a LaTeX feature, which is if I put this like that. Yeah, okay. So let's suppose n in n is positive. I guess I'll be a little, no, I won't be sketchy. I will be as formal as before. Notice that minus 1n plus 1 n plus 1 is equal to 1. Right, okay. So since n is positive, 1 divides n. In particular, that it's not 0. No, but 1 always divides it. Well, okay, so here's the thing. Like, we're getting, okay, this is, let's see, did I get the accent right for Bezu? Yeah, okay, that's the LaTeX way to add an accent to the next letter. Wait, what's the name of this result? So it is Bezu's identity, but like all we really have is that the GCD divides 1. So it's more like the proof, because this is in the proof, because we showed that every element of the set of integer linear combinations of the two numbers is divisible by the GCD. So the other thing is, since n plus 1, well, since n is non-zero, then the GCD is not 0. Oh wait, but that doesn't matter. It still doesn't matter. Like, the only number that divides 1 is 1. So since GCDs are non-negative, this implies n plus 1 equals 1. Okay, so there's that proof. There's another. And this is the one which is why it is that n is assumed to be positive. So by the Euclidean algorithm, n plus 1 is equal to n plus 1 mod n. See, we want to be able to divide by n. And n plus 1 mod n is equal to 1. Because we can subtract n from it to get 1, and then if we subtract more than that, we get a negative number. Oh wait, what if n is 1? Well, that's a little annoying. So, well, anyway. Yeah, no, okay, let's do the two cases. Oops, I forgot to close that $sign. But case 1 is n equals 1. And case 2 is n is greater than 1. So then n plus 1 remainder n is equal to 2 remainder 1, which is 0. So we're not done there. I just want to write something here. N plus 1 remainder n is equal to let's see, how can I argue this? Well, it's 1. Since 0 is less than or equal to 1 is less than n, because n is greater than 1. And n plus 1 is equal to the quotient, which is 1, times what we're dividing by, plus 1. Okay, we've got this. Hence, n plus 1 is equal to n0, which is equal to 1, 0, which is 1. Great. Oops, and then hence n plus 1 is equal to n1, which is right, okay, right, n1. And that's just 1. Let's say, well, yeah, it's 1. Because we could keep doing the Euclidean algorithm, right? But 1 is the only factor of n and 1. There's not really a point in belaboring that. Okay, since the conclusion holds for both cases, we are done. Therefore, the result holds since it. That was fine. Okay, well, that was a surprise little extra case. When you mod by this and n happened to be 1. But that's why it pays to be careful in math. Let's see. That wasn't a sentence. Okay, 9b. There exists a positive n and a prime p such that p divides n and p divides n plus 1. Well, that means it's a common factor, right? And that's the greatest common factor is 1, so p would be 1. But 1's not a prime. So we're going to disprove. So we'll disprove this. We will instead show that for all positive n in n, and all primes p such that, oh wait, what am I saying? There exists a positive, oh right. Then p divides n, does not divide n, or p, oh no, is that what I want? Oh, then, okay. You have to decide how far you're going to negate something. So I'm going to say it like this. So for all positive n in the natural numbers and all primes p, then it is not the case that both p divides n and p divides n plus 1. Because I want to show this essentially by contradiction. It's not actually called by contradiction. Like, to prove that something is not the case, you just assume that it is the case and you prove it, that a contradiction happens. There is a subtle difference, but doesn't really matter too much. Well, I guess it matters if you care about constructive logic. But we're just doing some classic number theory. So let's proof, disproof. I've never written that before. That's kind of fun. Okay. So, suppose n is in n and p is a prime. Assume we will show that we obtain a contradiction by assuming p divides n and p divides n plus 1. Okay, I'm just writing out what I said earlier. Since p divides both, then it is a common factor. Hence, by definition of greatest, by definition of greatest common, we don't call them factors here, we call them divisors. Because the factor is something that appears in a multiplicative expression, where a divisor is something that divides according to this definition. So it's by definition of greatest common divisor, p is less than or equal to n plus 1. By part A, we saw that n plus 1, I forgot the word positive. Not that it matters. Okay, we saw that that's 1. Hence, p is less than or equal to 1. Okay, here we have a little problem, and that is a prime allowed to be negative? And in lecture that was allowed. Sometimes they are not allowed to be negative. So and we want to be completely rigorous here. So one thing is, we did prove in lecture that actually it's that p divides the GCD that we can assume. I'll show you this way, and I'll move back to that. So let's do it this way. So I'll do two cases. Case 1 is that p is positive, and case 2 is that p is negative. 0 is not a prime, so we don't need to worry about that. Let's actually just cover all our bases here. So we've got this dichotomy. So then we can take this we have that, and by part A we saw that the GCD is 1, hence p is less than or equal to 1. But if 0 is less than or equal to p is less than or equal to 1, okay, but that means p equals 0 or p equals 1, but neither of these are prime. Okay, so that's the positive case, and that's the one that we'd rather have. Can we transform the negative case? So if we take our negative prime, we can take the negative of it. And also, so it's true that negative p is greater than 0, but it's also greater than or equal to 0. So furthermore, minus p divides n, and minus p divides n plus 1 by using minus 1. If we take the constant for the divisibility definition, we can multiply those by minus 1. Hence, we may apply case 1 with minus p in place of p. This is a little trick to reuse work. And by applying it, we reach a contradiction. So both cases resulted in contradictions. So they're done. Okay, yeah, so I was worried about p being negative for this. I guess I'll take this again. And we'll use a different result. And that is, so it's a common divisor, and by a resultant lecture, then p, then the GC, oh, let's see. Every common divisor divides the GCD. And then by part A, we saw that the GCD is 1, hence p divides 1. This implies that p equals 1 or p equals minus 1, but primes are, by definition, not units. Therefore, we have a contradiction. Yeah, that proves simpler. I just wanted to go through getting this all right because I wanted to show how that would work, how to use a previous case. So this is also something where you might see at this moment right here that without loss of generality, p is positive. And what that means is that if p were negative, then we can transform the problem like this and then just consider one case. Without loss of generality is actually a cases proof. Yeah, with this transformation, usually the transformation is obvious, but it's definitely obvious when written in this way. So in some ways that's better. The only trick here is for being logically careful, you want to make sure that, I guess, like it's a little sketchy using a previous case like this. So like what we're really doing is saying, if it were the case that p is greater than or equal to 0, then we can prove this. Alright, here, I'll show you what I mean. So we can say claim so then we get a contradiction. So this proves the claim, and then the space tops up. Let's see, is this? Okay, so then the way that this looks, so we apply the claim to get a contradiction, and then if p is 0, we transform the problem, or less than 0, we transform the problem. We may apply the claim with minus p to get a contradiction. So that's like sort of really the right form, because I was saying it was sketchy to invoke case 1 in case 2, because well, in cases they're all supposed to be completely logically separate from each other. Otherwise you can reach incorrect contradictions, potentially. Okay, so if p is greater than or equals 0, I think I'll leave it in this form. It does make it a little bit more complicated, but it also makes it more likely to be correct. I guess I don't need that v space because it's sort of built into the description. But I should say, oh, right. It is good to say that we're going to do cases, right? Okay, I'll leave it like this, and if you watch the video, then you saw how it used to be. Okay. Let's look at the next one. If n is positive, what are all the possible values for n, the GCD of n and n plus 2? So, it's not a proof. We saw before that n plus 2 is equal to n plus 2 minus n, which is n2, the GCD of n and 2. So, by the Euclidean algorithm, n2 is 2n mod 2. So let's look at two cases. The two possible values of n mod 2. So the second case is when it's 1, the first case is when it's 0. When it's 0, then where are we? N plus 2 is 2, and remainder 2 is 2, 0, which is 2. Then, now the second case, let's just copy paste that. 1, 1. Therefore, the GCD must be either 2 or 1. Okay, something to know. We showed that if we had a GCD and somebody told it to us, we could be like, is it a 2 or is it a 1? And then they'd have to say yes, because we proved that. Oh, right, I want to say, let's do it in set notation. But we didn't actually show that these are possible values. But it's not hard to see. Like, we just have to check. So, 1, 3 is 1, and 2, 4 is 2. So, it's easy to check, but it is something we technically have to do. There's another thing we can do here. Another way we could have done this is notice that 2 is equal to minus 1n plus 1n plus 2. So by the proof of the Bezier identity, we have that the GCD of n and n plus 2 divides 2. since GCDs are non-negative, then n plus 2 has to be a divisor of 2. And we still need to check that both values are possible. Okay, so for each possible value in C, come up with a condition that lets you predict what it will be. Well, the way we calculated it, it makes it sort of obvious, but I guess it's worth saying it. So, so to get n plus 2 equals 1, then n remainder 2 equals 1. That is, if so we get this when it's n mod 2 is 1. That is when n is odd. And we get n plus 2 is 2 when n remainder 2 is 0. That is when n is even. Put those in parentheses because we never really defined even and odd other than in passing. But it is just, it's really just defined by this, I guess. Or actually, one definition of even is that 2 divides it, and odd is a number that's not even. And then one can prove that if a number is odd, so if it's not even, then when you take the remainder mod 2, you get 1. Okay, 10. For all non-zero n, if each exponent in a prime power factorization of n is even, then n is a square. Okay. So to set this up, we need a prime power factorization. So this is mostly a notationally challenging problem. So it's a non-zero n because those are the only ones that have prime power factorizations. So let's let p1 through pk in n, in n be primes, and c1 through ck, well, let's let k be an n, let these be primes, and let c1 through ck, I said that we never defined even, and here we are using it. But be such that n equals p1 to the c1, p2 to the c2, c dots. Actually, LaTeX will figure that one out. Dots. pk to the ck, which exist because n is non-zero. The which referring to all these numbers. One thing to notice is that k is actually that's a L dots. I want a C dots for center. Okay. Right. So I forgot what I was going to say. Oh yeah, k can be 0. That happens when n is 1. because it's the product of no primes, and the product of no things in a row is 1 by definition. Right, so now suppose each for all I in the range 1 through k that Ci is even, which is to say that 2 divides Ci. By definition of divisibility, for each of these I, there exists a di. Everything's positive, so we can assume it's a natural number, such that Ci equals 2di. Okay. Hence, we can substitute those in. So I'm not being very careful here, because really I should be doing some sort of like a I should be doing induction of some sort, but let's prove this next part by induction, just to be careful. So the claim is that for all k, or no, not k, for all L, for all 0 is less than or equal to L is less than or equal to k. No, I'm confusing myself. The claim is just that n equals p1 to the d1, p2. Ooh, that looks wrong. Okay. So that's why it's nice to have a little bit of editor support for LaTeX. It's nice how it's exponent like that. So yeah, like this is just supposed to be, we've got all these, it's basically interlaced in a way. Like when you're raising to the 2d power, then it's to the d squared. So we're just wanting to do this to turn it into a square. Like, this is the claim, that we can take all these 2's and pop them out. And if we believe in our, yeah, like we technically need to do induction for this. Because what does that dot 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 even mean? Okay. We will show this by induction with the statement P of L okay. I want to actually say this so that I can set my induction up. I don't want n in this. And my induction statement is going to be on k. Okay. So the base case is when k is 0, right? And this is the product of no things. So we're wanting to show that 1 equals 1, which is certainly true. Now we need the inductive step, which is k is greater than 0, and we assume that if k is 0 and this is true, then it's true with one more term. I find it's a little weird using the same letter k as before, but as long as you're following along, it's fine. It's just there's nothing wrong with it, just it's a little weird. So let's see how this is looking. Also, I think I've been using bold for this. Okay, so we got the base case, and then the inductive step is if k is greater than 0 and the thing, then it's true for k plus 1. Okay. So this is, so, and, I'm going to change this to supposing. That way I don't, I've just been using suppose to mean like introduce this thing, where for all is more of part of a statement, and then you need to like suppose afterwards. It's not really particularly set in stone, but it's been working so far. Okay, let's calculate. So we want this left-hand side, and we'll do equational reasoning. Oops, copied a little too much. So I'm going to add parentheses here, because then by hypothesis we can replace the other side, or we can replace it with the other side of that hypothesis. And then what? Well, we can also use the exponentiation law, like so. Here, to give you a look at what's going on here. So we have the left-hand side of what we want to show, and then I indicate in parentheses what we wanted to replace with the hypothesis, right-hand side, and we use this exponentiation law, or the power law. And then we can, since it's a product of squares, we can turn it into a square, turn it into that. And then remove those inner parentheses. Okay, and let's add a comma, which is what we wanted to show. Okay, and then this completes the induction and the proof of the claim. And I'll add a little bit of space, because for some reason paragraph breaks don't look right here. I'll figure that out sometime later. Okay, so now applying the claim, we have that n is that which is that and so therefore n is a square. You know, that kind of belabored the point. Like, we're just like being careful of proving it. Like, the point really is just that we can pull all those 2's out. But, you know, can we? So that's why I did it carefully with induction. Also, it doesn't hurt to see yet another induction proof. What's that comma doing there? I think I was going for this. Yep, okay. Yeah, like this direction is like the super easy one in a way. And like, I really just belabor it. It does turn out that the converse is true too. For every non-zero n, if it's a square, then each exponent in the prime power factorization is even. And I'm not sure why I didn't ask that one. It must have been a mistake. Okay, well, let's prove this one. We want to know that n times n plus 1 is not a square. So suppose n is in n, and we're trying to show it's not a square. So what was my wording before for this? Because for sake of contradiction means something slightly. We'll show we obtain a contradiction. I mean, it's like the same thing, but has just a shade of distinction. So we will show we will obtain a contradiction by assuming that n times n plus 1 is a square. Yeah, so see, this is where, if this were the other way, it'd be useful. Because we're assuming it's a square, but this has the conclusion that a number is a square. So either we can prove the converse of this and use that, because if it were a square, that would mean that each power in the prime power factorization would be even. But let's see. These the numbers. So n and n plus 1. We showed the GCD of them is 1, so they have no factors in common. I'm suddenly feeling confused. Maybe that's from almost 2.5 hours of doing this. Like, okay, so there's this proof I have in the back of my mind, which is that if it were a square, well, I'll just write it out as we go. So by definition of being a square, there exists an m in the naturals such that m squared equals n times n plus 1. So one thing we know is m is not 0. Since I'll write this as a claim, I guess. Or have. M is not. Let's bold it. So M is not 0. If instead M equaled 0, okay, I'm just trying to say that n times n plus 1 is non-zero, so I'll just write all these claims out. Actually, what I want is that it's 2 or more, right? Because if n is 1, then it's 1 times 2. This is because 1 is less than or equal to n, and 2 is less than or equal to n plus 1. So we can multiply these. Oops, that should be a C dot. Let's see how this is looking so far. Okay, so what else do I want? I really think I want m is not 0 or 1. I want that to be true for m2. So if instead m were less than 2, then we would have m equals 0 or m equals 1, but if it's instead less than 2, then because it's an integer, it would be less than or equal to 1, and then, well, it's a natural number in particular, and then m squared would be less than or equal to 1. But m squared is n times n plus 1, which contradicts the previous claim. So that was a little contradiction proof. Okay, so where am I going here? What I was thinking is, we can use the fact that every number has a prime divisor. Probably. Probably. Yeah, okay. So since 2 is less than or equal to m, then there exists a prime p in the natural numbers such that p divides m. We need the 2 is less than or equal to m because otherwise m would be 0 or a unit, and they don't have prime divisors. Well, 0 has a prime divisor, but every prime, but 1 is a problem. So we just did these inequalities to get us into this situation. Okay, so hence p squared divides m squared. Because you can, I think that was a homework. Wasn't that homework? Just already forgotten. Yeah, we should cite it. Yeah, that's 5. Because, yeah, we're using the same one for each. Okay. So, and thus, p squared divides n times n plus 1. Where is this going? What am I doing? Oops, I didn't mean div, I meant mid. Okay, so one thing is, because P is prime, and this is where I've been going, or I don't know if this goes anywhere, but since P is prime and it's dividing a product by the primality property, P divides n or P divides n plus 1. And so P squared will divide n or P squared divides n plus 1. Huh, okay, maybe we can use the previous problem. This is making it look like I have no plan when I make these, but I do. It's just, it's been a week. So maybe this is what I had in mind the whole time. This other thing, okay. Okay, we have we assume it's a square. And so they're or maybe we're not really going to use the previous problem. It's just sort of a reproof, I guess. So we've got this. I think we didn't need any of that other stuff. No, it's nice to have this because I just need to think. So, we got this prime that divides m, and so we know that P squared divides m squared, and then P squared divides this product. Instead of there exists, let's change this to claim. For every prime P in n such that P divides m, all this other stuff, we will need it, I believe. But we just want this other statement first. So for every prime that divides m, then P squared divides n, or P squared divides n plus 1. Let's try this. So let's try a proof environment in here. Yeah, that seems good enough. Okay, we want to prove this claim. So suppose P in n is a prime such that P divides m. So we got this there. And then also, since P divides P squared, then P divides n plus n times n plus 1. Hence, by primality, P divides n or P divides n plus 1. So let's do cases. P divides n. And case 2, P divides n plus 1. So when P divides n, since by what part? Problem 9a. We have the GC of n and n plus 1 equals 1. then p does not divide n plus 1. Now, what I want to say is that since p does not divide n plus 1, that means that p squared has to divide n. Why can we say that? Well, one thing is, so p n plus 1 equals 1, the coprime. There is a result in this in the book, which is that if a number divides a product, well, actually, if we can get this, because if p squared in n plus 1 had a GCD, it would be a divisor of p squared, and the only divisors are 1 and p because it's prime. And also p, yeah, 1 p and p squared. Well, definitely p does not divide n plus 1, so p squared. Great. So another thing is, so if p squared divides a product, but the GCD with one of the two numbers in the product is 1, then so thus, since p squared divides n times n plus 1, then p squared divides n. Well, that is a result. I'm just trying to remember if we proved it or not, but it is in the book. Okay. Now for this, notice that, well, let's just do it again. And we'll use the keyword similarly. So similarly, p squared n equals 1, and thus p squared divides n plus 1. Using the same stuff, we're just kind of replacing, we're swapping n and n plus 1. Okay, since we should say we proceed by cases, therefore the claim holds because it held in both cases. Should we number these? May as well, right? Can't make it less clear. I was just thinking, do we do proofs for this too? But, and so previous claim, let's say, contradicts claim 1. Also, to make this look like a theorem, usually theorems are italics. Okay. We've got this claim. For every prime, it divides, the square divides one of the two. Is that enough? Because where is this contradiction? You know, I think this was not strong enough of a claim. What I really want is if I have a prime power, I think. So let's see if we can fix it. So every prime p in n and k in n such that p to the k divides m. Let's say positive. I don't actually know if I need positive. Just seems like it would make it a little easier. Okay, so I want to say then the square of that prime power divides one of the two. Let's think through this again. So we have n as a natural number, and we want to obtain a contradiction by assuming that this number is a square. So it's a square, that means that there's some number that when you square it, we get n times n plus 1. And so n and n plus 1 have no factors in common. And since they have no factors in common, that means that each of the prime powers that show up in m have to then show up completely in n or completely in n plus 1. But squared. And then what we're going to show is that n is a square. And n plus 1 is a square. Okay. Since then they're both squares, that means n has to either be then n has to be 0, because there are no consecutive squares except for 0 and 1. Okay, so claim 1 and claim 2, we're going to need those because that's why non-zero is here. Because if it's 0, 0 times n plus 1, that's 0, that's a square. Okay, so we have this thing that we're doing right now, which was we're showing that whenever we have a prime power, then it appears in one of the two. Okay, so let's have a prime. So we have p and k such that p to the k divides m. Hence, 2k, p to the 2k divides m squared, and so p to the 2k divides n times n plus 1. Since p certainly divides p to the 2k, because k is positive, and that's why I wanted that, then p divides n times n plus 1 by transitivity. So hence, by primality, p divides n or p divides n plus 1, and we proceed by cases. And both cases are very similar to each other. So the first one is that p divides n, and by 9a we had that the GCD is 1. So then p does not divide n plus 1. So p to the 2k and n plus 1 is 1. For a similar reason as before. So since p to the 2k divides n times n plus 1, by that theorem that's in the book, divides n. Okay, and then similarly, we got this is 1, and then 2k that divides n plus 1. Therefore the claim holds. Now here is what we will do. It's funny, yeah, part A really is relevant. Okay. So let m equals p1 c1 dots. Oops. So I'm writing down a prime power factorization. Oh, I've been using k's in this problem, so. And I'll use L for the upper bound. So let's let this be a prime power factorization of m. Since 2 is less than or equal to m, then there exists a prime divisor of m, so L is greater than 1, or greater than or equal to 1. Because if L were 0, then that would be the empty product. That's when m is 1. And we also want m to be non-zero, which is non-zero by claim 2. By the same claim, just figuring out how I want to say it. Okay, it's non-zero since that. Okay. But why am I actually don't remember why I thought I needed to do that part. I'm really not sure. Right, okay, so here's what I want to do. I want to use this claim, and since by claim 3, for each I between 1 and L, we know that pi to the ki divides n, or it divides n plus 1. So now there's a little bit of a notation challenge. Because I want to basically separate all these primes into those that divide those that divide n and those that divide n plus 1. So here's how I will do this. Okay, rearrange the primes in the factorization so that there is a, what letter shall I use? M? No, I already have M, and I have N. I use K. H. Such that for all, like I'm just saying we like sort it so that for all 1 less than or equal to I less than or equal to H, then Pi to the Ki divides N, and for all H plus 1 less than or equal to I less than or equal to, oh wait, might be 0. Yeah, we'll talk about that in a moment. Less than or equal to N, oh, L, then Pi to the Ki divides N plus 1. Also, I forgot some 2's. Let's put all those 2's in. Let's see what this looks like. Okay, so let's let M have this prime power factorization. By claim 3, for each I, we know that when we square that prime power, it divides n or n plus 1. If we rearrange the primes in this factorization, then we can do so that there's some cutoff point h, such that when I is from 1 through h inclusive, so h is allowed to be 0 in case this never happens, then Pi to the 2Ki divides n, and also for all I above this cutoff point, so h plus 1 through L, and this is also why h is allowed to be L, so that this might be empty, or there are no i's, then it divides n plus 1. Okay, that's one way to say it. I guess I'll go with that. Okay. So, what we have, hence, I sure hope this is going where I hope it. I think it is. So let's write this out as so m squared is this thing squared and let's just split it up. So we've got ph to the kh squared, ph plus 1 to the kh, oops, okay. so what I'm trying to do is say that this is n, and this is n plus 1. Okay, so relying on our previous work in the previous problem, then we can bring all those 2's in. This isn't a hence. Let's just say we have where this divides n and this other one divides n plus 1. Now, I really don't know if I'm doing this the best way anymore. It's so, because don't be scared if this seems impossible to come up with. Maybe we'll simplify it once we figure it out. So, why do we know that? One thing we should say is that we want these primes to all be distinct. Because I want each one to be co-prime to each other. So the GCD of PI and PJ is 1 when I is not equal to j. So, because when you have co-prime things, okay, then you can multiply them together. So if two things divide the same thing and they're both co-prime, then their products divide it. And that's the fact I'm using here. But technically that needs another induction. I really don't want to do that right now. It's been almost 3 hours. So, by claim 3, for each I it divides one or the other. So we'll rearrange it so that the first half divides the first and the second divides the second. Since okay, so this is using the fact that if A mid C, B mid C, and AB is 1, then AB mid C. Such a cheat. Sorry about that. I'm saying we can use induction to show that we can prove this. It's just going to be more work. It's that so if A divides C and B divides C, so namely each of these terms divides n, so their product divides n because they're all co-prime to each other. Anyway, so we're not being rigorous enough for me. But if, I don't know, like anyone who knows how to do induction should be able to fill this in. I'll just apologize. Okay. Now what? Likewise, since these two things are coprime, then what we have is their product divides. Their product. Oh, we don't need the coprime part. But we already had this. Look, so what I'm trying to do is I want to show that n divides this, so the reverse way, because then by anti-symmetry they're equal. So how can I show that's equal? Probably a lot easier way to prove this. Like once they like stand up, walk around, I'll be like, why did I just spend the last however long doing it this way? Okay. So we've got these two numbers that we have a number that divides n and a number that divides n plus 1. And we know that when we multiply them together, we get a number that just equals n times n plus 1. So like it's one of those things where like it's just obvious that these are equalities because of that, but I'm struggling to put into words the exact reason why that is true. I felt like so it's not so hard to do, but I got tired by this point. Okay, let's try this again. So we got some number, really it doesn't matter what it is, divides n. Some other number divides n plus 1. And we know that if we multiply them together, we get this, just by multiplying. That's what exercise? Problem 5. But we also already knew that because this is an equality. So maybe the way forward is to use inequalities. So it's because everything's positive here. So we can turn those into less than or equal to. So suppose for sake of contradiction that either this were a strict inequality or that were a strict inequality. Then we would have that when we multiply them, we get a strict inequality. However, the left-hand side is m squared, and m squared equals n plus 1. So we have a contradiction. Let's see, does that work? So we got these two inequalities, and suppose for sake of contradiction, we have a strict inequality, and then by multiplying, we have that. But the left-hand side is m squared, and m squared is n times n plus 1, so we have a contradiction. Okay. Thus, we have our equalities. Okay, we got these we've got these equalities now. So by what letter was it? By part A, it's a square. Both n and n plus 1 are squares. Cool. Hence, there exists. Let's let. Okay, I need new letters. Let's say A and B. Be such that n equals a squared and n plus 1 equals b squared. Now I'm just trying to get a contradiction now. So how do I do that? Oh yeah, and isn't that a lot like confusing? We had a contradiction proof inside a contradiction proof, but it works as long as we're careful. Probably better to just put that into a claim to make this clear. But yeah, I should do that. So claim. These are equal. I guess this is claim 4. We're going to delete some claims. Okay, so by part A, this claim 4 implies that both n and n plus 1 are squares. Yeah, that's clear, right? Okay, so hence, what we have is that a squared plus 1 equals b squared. Let's make that flow better. So 1 is b squared minus a squared, which is b minus a, b plus a. So when you have a product that's 1, the only divisors of 1 are plus or minus 1. So how do I want to say this? There's probably a better way, but oh right, here's one thing that we know, just to simplify it. Note that b is greater than a, because if b equal to a, well then n would equal n plus 1, which is absurd. And if b is less than a, then n plus 1 would be less than n. So I'm just going to say note that. And that's one of those little puzzles in a proof that's up to the reader to figure out. Just by the way, when a mathematician says something is obvious, it just means that with some thought you can figure it out yourself. It doesn't require any like deep creative insights, just some work. Okay, so we've got this. So since b minus a is greater than 0, then b minus a equals 1 and b plus a equals 1. Adding these equations, we get 2b equals 2, so b equals 1, hence a equals 0. But then n equals a squared equals 0 squared equals 0, and we assume that n was positive. Okay, this last part of the proof was just the thing I said now quite a while ago, which is that when you have two squares that are 1 away from each other, it has to be 0 and 1, and so this just proves that these squares are 0 and 1. But we assumed it was positive, so that can't happen. Okay, what did we not use? Did we use claim 2? We did not. Did we use claim 1? We did not. Let's just delete them. We don't need them anymore. So let's renumber this. That's a long proof. Let's look through it. So for all non-zero n times n plus 1 is not a square. So let's suppose we have an n, and obtained by contradiction by assuming that it is a square. And then by definition there's some m where m squared is that. And so then what we do is we look at every prime power that divides m and then conclude that, well, since by a previous problem they're coprime, that prime power must divide one or the other. So, proof of claim 3. That's not right. Proof of claim 3. Proof of claim 1. Okay, so, and we did that by supposing that we had a prime power that divided m, and then so by a previous problem we could square it, and then, well, it divides this product, and then less strongly just the prime divides that product, and so then by primality p divides one of them. And then, okay, then cases. We should have a colon. So if it divides the first one, then it doesn't divide the second, and so the prime power doesn't divide the second. Right? Okay, yeah. And then that prime power, since we're assuming that it divides this product, then it had to have divided the first one. And then we do the same thing because it didn't matter what these two numbers were. We can just swap their roles. Okay, now we take a prime power factorization of m, and we have all these distinct primes. I'm not sure if, yeah, that did matter. And by claim 1, for each I, we know that the prime power when squared divides one of the two. And then we rearrange all the numbers so that there's some cutoff point h where all the first ones correspond to n and all the second ones correspond to n plus 1. And we use the fact that whenever two numbers that are co-prime divide a third number, then their product divides that third number. And we do it inductively for these products. Okay, so what next? So hence, since since n and n plus 1 are positive, we can turn these divisibilities into less than or equal to's. And then we say that it's actually an equality, because if it weren't, where one of them or both are less thans, then we can take their product and get that the product is less than, but the left hand side is m squared. But m squared is this product because that's what it was defined to be. So that's a contradiction. Okay, so they're equal. And then once we got this equality, then by the previous problem, they're both squares. And so we write them as squares, and then do some algebra to say that, well, n is 0, but n's not 0. So that's that. Okay, I'll let you know if I come up with a better solution, or what I must have had in mind before. So let's just skim through now that we've finished. Good number of problems here. We've written out a lot of detail today. Yeah, it's been a while since I remember that we did that. In some ways this was fun. Otherwise it's been long. I hope seeing the struggle, or like, you know, seeing the thoughts, seeing the writing things up, hopefully there's something of value in here. If not, well, you don't have to watch the video. And anyway, yeah, well, see you next time.